2 telescopes, 2 separate years, 1 matching signal at 20 parts per billion. That was the claim that reshaped the search for alien life overnight. Every major observatory took notice. In September 2020, astronomer Jane Greaves announced a detection at Cardiff University. Phosphine gas, sitting in the clouds of Venus. For decades, one rule held firm in astrobiology. Phosphine on a rocky planet was supposed to be a fingerprint of life. Not a hint, not a maybe, a fingerprint. Astronomers had built entire search strategies around molecules like it. Telescope time on major instruments gets allocated years in advance, partly based on which molecules seem worth chasing. That rule is the alien life assumption astronomers just shattered. It said phosphine on a world like Venus was a clean, unambiguous signal of biology. Astronomers had leaned on similar logic before, scanning other worlds for the same telltale chemistry. That belief collapsed once researchers found something no one expected. Raw volcanic chemistry alone could plausibly make the exact same molecule. If a volcano can fake a biosignature, the entire search method needs a second look. Telescopes across the world had been calibrated to treat this exact molecule as decisive. Nobody had seriously modeled a scenario where geology alone could produce it in these amounts. Scientists felt sure enough in 2020 to announce a possible sign of life. So why are many of them unsure the gas is even there today? What made phosphine specifically feel like airtight proof in the first place? A volcano, it turns out, can produce that same gas without any biology at all. So what does that mean for every other sign of life ever claimed in space? Venus's surface is a furnace. 92 times Earth's air pressure crushes down on every rock there. That's roughly the same crushing force found nearly a kilometer beneath Earth's oceans. Temperatures hit 465 degrees Celsius, hot enough to melt lead outright. The Soviet Venera 13 lander holds the current endurance record on that surface. It survived 127 minutes before the crushing heat destroyed its electronics. Even Venera 13's camera lens cracked from the pressure within its first hour. Soviet engineers built its outer hull from solid titanium, the only metal that held. Its instruments still failed well before the mission's planned duration. Every Venus lander since has faced the identical problem. No spacecraft has lasted longer down there since, but climb 50 to 60 kilometers up, into the clouds, and the story flips completely. Venus's atmosphere there is mostly carbon dioxide, laced with thick droplets of sulfuric acid. Temperatures there ease to a mild 30 degrees. Pressure drops close to what we feel at sea level on Earth. For decades, scientists have speculated this narrow band might be Venus's one livable layer. Carl Sagan floated the idea back in the 1960s, long before any spacecraft confirmed the conditions. A thin shell of almost Earth, floating above an inferno. Astronomers had scanned this cloud layer for decades. They were hoping to catch exactly this kind of signal. It was exactly there that Greaves's team caught theirs, first with the James Clerk Maxwell Telescope in Hawaii, back in 2017. That single observation alone wasn't enough to convince the team. Then again in 2019, with the Atacama Large Millimeter Array in Chile. That facility links dozens of radio dishes high in the desert. Together, they work as one giant telescope. Their early estimate placed the concentration at roughly 20 parts per billion. On Earth, by comparison, sunlight destroys atmospheric phosphine almost as fast as it forms. Two independent instruments, 2 years apart, had landed on the same reading. That single number would end up carrying the whole debate on its back. Here's why that number mattered so much. On Earth, phosphine comes almost only from 2 sources. Anaerobic microbes make it, buried in oxygen-starved mud and swamp gas. Industrial factories make it too, inside controlled high-heat chemical reactors. The gas itself is famously unstable. It reacts with oxygen almost the moment it's exposed to air. That's part of why finding any of it at all counts as unusual. Something has to keep replenishing the supply, faster than sunlight destroys it. Almost nothing else produces it in meaningful amounts. Astrobiology's working assumption, backed by earlier published research, was stark and specific. A 2020 paper reviewing possible biosignatures had explicitly listed phosphine. No known abiotic source, it claimed, could explain a detectable signal on any rocky world. This gas supposedly had no known lifeless pathway able to explain what Greaves was reporting. Find enough of it, and life became almost the only explanation left. So her team tested every alternative they could find, one by one, before publishing anything. Lightning as a source, ruled out, far too weak to generate meaningful concentrations. Meteorite delivery from space debris, ruled out too. Impacts happen far too rarely to sustain the levels observed. Ordinary photochemical reactions in Venus's atmosphere would produce far less phosphine than what they'd measured. They even aimed their telescopes at Callisto. That's a moon of Jupiter, where phosphine shouldn't exist at all. They found nothing there, exactly as their model predicted. That negative control gave their entire method a credibility check most single-planet studies never get. Reviewers at the journal reportedly pushed hard on this exact point before accepting the paper. Every negative result mattered as much as the positive one. No ordinary explanation remained standing after all that testing. Every chemical pathway they knew had been checked and dismissed in turn. So the paper reached a conclusion rare for peer-reviewed science. Either some unknown chemical or geological process was quietly at work on Venus, one nobody had previously considered. Or, they wrote cautiously, hedging every word, it was life. One sentence detonated across the world's press within hours, splashed across front pages everywhere. Newspapers ran the story on front pages within a single news cycle, across dozens of countries at once. Some outlets softened the careful hedging in the original paper into outright confirmation. Astronomer Vladimir Lira called the detection method thorough. ALMA specialist Nienke van der Marel agreed with him publicly. 2 telescopes, built by different teams using different receivers, landing on the same false positive by coincidence. That seemed statistically unlikely, both said. Their support carried real weight in the field, given both scientists' technical standing. For a few months, the biosignature framing held its ground almost unchallenged. Headlines kept multiplying, and public fascination with Venus spiked overnight. Search interest in the planet reportedly surged to levels not seen in years. Then the pushback arrived fast. By November 2020, a team led by Geronimo Villanueva filed a formal rebuttal. He worked at NASA's Goddard Space Flight Center. His specialty was exactly this kind of atmospheric spectroscopy. It went straight to Nature Astronomy's Matters Arising section. Their argument was blunt and specific. They used their own independent reduction of the same ALMA dataset. Greaves's team, they claimed, had misidentified a spectral line entirely. What looked like phosphine, they argued, was actually sulfur dioxide. That's a molecule already common throughout Venus's atmosphere. Volcanic outgassing produces it there constantly. In far greater volume than any biological process on Earth, the 2 gases absorb radio waves at close frequencies. They blur together, especially once you account for how Venus's upper atmosphere shifts the signal. Villanueva's group didn't stop at doubt. They explicitly called for the original paper's retraction. That's a rare, aggressive move in astronomy. Most disputes get resolved through quieter follow-up papers, not public calls for retraction. Villanueva's team was making clear how serious they considered the error to be. A second independent line of evidence followed close behind, using no ground-based telescope at all. Researchers went back through historical data from the Venus Express orbiter. That European Space Agency mission had orbited Venus from 2006 to 2014. It gathered years of atmospheric readings. Nobody had reanalyzed its readings for this purpose yet. They searched that dataset specifically for phosphine. They found nothing resembling it, a completely different dataset, gathered by a completely different method. It pointed the same direction as Villanueva's critique. One line of evidence was chased in real time. Its instruments were built to hunt this exact signal. One was pulled from an old archive nobody expected to matter again. It had been gathered for entirely different goals, years earlier. The fight didn't end there. It mutated instead into something stranger. As the dispute dragged into 2021, Greaves's own team went back through their data. They quietly revised their estimate, down from 20 parts per billion, down to somewhere between just 1 and 5 parts per billion instead. That correction didn't settle the argument outright, but it reopened a door the original paper had swung firmly shut. At 20 parts per billion, volcanism alone couldn't plausibly explain the numbers. At 1 to 5 parts per billion, the math suddenly looked different. A concentration that low was suddenly light enough for something else entirely. Ordinary volcanic activity, an idea earlier estimates had made seem almost impossible. Here's the turn almost nobody saw coming. In July 2021, Ngoc Trong and Jonathan Lunin published a direct challenge. Both worked at Cornell University. They wrote in the Proceedings of the National Academy of Sciences. It's one of the most cited journals in science. Volcanism, they argued, had never really been off the table. despite how the original 2020 paper had framed it. Earlier papers had dismissed it too quickly. They relied on outdated assumptions about how much phosphine an eruption could realistically produce. Truong and Lunin modeled the reaction directly. They used known rates of phosphide weathering, measured in Earth laboratories. Phosphide minerals sit buried deep in Venus's mantle, stable for eons under normal pressure. An eruption violent enough could blast that material upward, straight into the clouds above. There, it reacts with sulfuric acid already saturating the atmosphere, producing phosphine gas directly. Every step uses ordinary chemistry, tested already in laboratories on Earth. No biology required anywhere in that process. The phosphine is not telling us about the biology of Venus, Lunine said. It's telling us about the geology. 6 words, reframing an entire scientific mystery. That single hypothesis quietly demands something specific of Venus. For volcanic phosphine to work, Venus needs active volcanism, or very recent explosive eruptions. Separate radar surveys of Venus's surface have independently found lava flows. They look startlingly fresh, geologically speaking. They show none of the erosion older flows typically display. Venus has no rain, no rivers, no strong wind erosion. That makes surface freshness itself a meaningful clue. Radar imaging from the Magellan orbiter had hinted at this decades earlier, without proving it. Geologists had long debated whether Venus's volcanoes had truly gone quiet. This phosphine dispute, oddly, started supplying them with fresh ammunition. A search that began as a hunt for alien life had shifted entirely. Without anyone planning it, it became evidence in a different fight. Is Venus still geologically alive right now, beneath all those clouds? That question didn't stay settled for long either. In September 2024, a new observing run targeted Venus once more. 5 years after the original controversy began, a new JCMT observation campaign used different data reduction methods than the disputed 2020 analysis. This one was designed to sidestep the sulfur dioxide confusion. It reported detecting phosphine again, in that same cloud layer. This time the concentration measured roughly 300 parts per billion. The altitude, 55 kilometers, right inside that temperate band scientists had speculated about for decades. That's more than 10 times higher than the revised 2020 figure. A huge jump by any measure. 2 research teams, using the exact same telescope, reached different conclusions. The difference came down to processing choices alone. That alone says something about how fragile these detections really are. 5 years of argument, and still no resolution. The most basic question had no settled answer. Was the gas even there at all? You might assume a dispute this messy was a one-time fluke, unique to Venus. It wasn't. The same story played out 3 years earlier, on a planet trillions of miles away. In 2023, researchers reported a possible detection of dimethyl sulfide. On Earth, that molecule is assumed to come only from biological processes, mostly marine phytoplankton. It gives sea air its distinctive smell. This time the location was Exoplanet K218b, a world first identified years earlier by the Kepler Space Telescope, a world roughly 2.6 times Earth's radius, with about 8.6 times its mass. It orbits a red dwarf star some 124 light-years from Earth, far beyond any spacecraft humanity has built could reach. Excitement followed almost instantly, exactly like it had with Venus. Then came the same doubts, right on schedule. Could James Webb Space Telescope data even distinguish that signal from ordinary methane? Were there lifeless sources for the molecule too, ones nobody had ruled out yet? Researchers pointed to potential photochemical pathways nobody had modeled carefully before this specific claim. New gas, different star system, same exact doubt playing out on a much larger stage. Think about what this whole saga really resembles at its core. Picture a detective who finds one fingerprint at a crime scene. At first it looks like proof one specific suspect was there. Fingerprints, after all, are supposed to be unique markers, beyond argument. Then a forensics review raises a question nobody asked before. Maybe that print isn't a fingerprint at all, just a smudge from a common substance that happens to look similar. And even if it really is a genuine print, one more finding changes everything completely. Maybe the suspect never actually left it. An entirely innocent person could have left an identical mark, under conditions nobody had considered. That's the phosphine story in miniature. The evidence was treated as proof. A reanalysis then doubted the mark was ever real. Then a separate discovery showed an innocent process could produce the identical mark. No crime involved at all. The case never technically closed either way, and that's exactly the point. Every one of these threads is about to converge into a single answer. Walk back through what actually happened, in order, and the shape of it becomes clear. Greaves detected her signal in 2020, then checked it against two separate telescopes. She ruled out every ordinary source she could test, from lightning to meteorites. Early scientific confidence followed, voiced by both Lyra and van der Merel. Both found the method convincing. Villanueva's sulfur dioxide rebuttal landed that November. It used his own independent pass through the same raw data. Venus Express data, an entirely separate spacecraft record, backed that rebuttal up independently. Greaves's own revised numbers then reopened that door. Trong and Lunine walked through it in 2021, proving eruptions alone could make the gas. That theory then became evidence in a separate debate. Is Venus's crust still geologically active today, this year, right now? New 2024 data reignited the whole question instead of closing it. Early certainty gave way to doubt. Doubt gave way to a plausible, lifeless explanation. That same arc played out again almost immediately on K218b. None of this proves Venus is lifeless, not even close. It doesn't prove the opposite either, to be fair. Both extremes overstate what 5 contested years of data actually support. The honest answer sits somewhere in the uncomfortable middle. What it proves is quieter, and far more important for every future claim like it. For decades, astrobiology ran on one premise: certain molecules, the thinking went, are clean messengers from life, detectable across space, with total confidence. The Venus phosphine dispute revealed that premise to be a local, Earth-shaped assumption, not a universal law of chemistry. A molecule treated as an open and shut case here at home turned out differently elsewhere. It had a plausible volcanic alibi on another world, one nobody had considered seriously until the numbers demanded it. And that same pattern resurfaced almost instantly. A different molecule, a planet 124 light-years away. Every rocky world carries its own unfamiliar chemistry, its own volcanic history, its own atmosphere. Assumptions built on one planet's habits rarely translate cleanly to another's. Future biosignature claims will need an exhaustive list of every lifeless explanation, checked before any headline runs. Jane Greaves is still watching this argument unfold, 5 years after her first announcement. She has revised her own numbers twice since that first headline, each time in response to new counter-evidence. The dip she found in that spectrum, back in 2017, hasn't been confirmed since. It hasn't been fully disproven either. It simply sits there, unchanged, exactly where Jane Greaves first found it in 2017. A small dent in an old radio signal, refusing on its own to close the case on alien life.